This is a recast of the 6,200-word piece, Binary Weight Networks, BWNs, from schneepat.com. The article discusses binary weight networks, BWNs, a type of neural network architecture that uses binary values for weights. BWNs offer computational efficiency, reduced memory requirements, and energy-efficient implementations. They have shown promising results in image recognition, natural language processing, and autonomous systems. However, there are challenges related to training and precision that need to be addressed. Future research areas include enhancing training efficiency, exploring integration with emerging technologies, and investigating specialized domains for application. Let's listen in.
Today we're talking about binary weight networks, BWNs, which are a type of neural network architecture that use binary values for the weights of connections between neurons. This approach has gained a lot of attention in recent years due to its computational efficiency and simplification of memory requirements.
That's right. In traditional neural networks, the weights are usually real valued, which demand significant computational resources. But with binary weight networks, the weights are limited to binary values, either +1 or -1. This binary nature allows for reduced precision computations, making binary weight networks especially suitable for resource-constrained devices.
Absolutely. BWNs have several advantages over traditional deep neural networks when it comes to computation efficiency and memory usage. By representing the weights in a binary format, BWNs drastically reduce the storage requirements while maintaining a high level of accuracy.
And this reduction in storage requirements means that BWNs can perform computations more quickly and efficiently. This makes them ideal for applications that require real-time processing or operate under resource-constrained environments, such as mobile phones or I/O devices.
Exactly. And another advantage of BWNs is that they simplify the training process by eliminating the need for backpropagation. This further contributes to the network's overall efficiency.
That's a great point. The simplicity of binary weights enables energy-efficient implementations, which is crucial for devices with limited power resources. And this is why BWNs are becoming increasingly popular in various fields, including image recognition, speech processing, and natural language processing.
Right. BWNs have shown promising results in these AI applications and are an area of active research and development. They offer faster execution times, reduce memory footprint and computational complexity, and enable energy-efficient implementations.
Absolutely. The concept of BWNs dates back to the late 1980s when preliminary research was conducted on using bipolar weights. Over time, advancements in hardware, algorithms, and the need for energy-efficient computations have fueled the development of BWNs.
It's fascinating how technology has evolved to make BWNs a viable alternative to traditional neural networks. The use of binary weights instead of floating point values reduces memory storage requirements and speeds up computation.
Yes, and it's important to note that BWNs achieve comparable accuracy to their real-valued counterparts while operating with significantly reduced computational and memory costs. This makes them a promising solution for resource-constrained systems without sacrificing the quality of their predictions.
Absolutely. The architectural features of BWNs, such as binary weights and binary activations, contribute to their efficiency and robustness against adversarial attacks.
That's right. BWNs are able to achieve comparable accuracy to traditional neural networks while operating with reduced computational and memory costs. This combination makes them an attractive option for various applications.
In conclusion, BWNs offer significant advantages over traditional deep neural networks in terms of computation efficiency, memory usage, and energy efficiency. By representing weights in a binary format, BWNs reduce storage requirements while maintaining accuracy. This makes them ideal for real-time processing or resource-constrained environments.
And with advancements in hardware and algorithms, BWNs are becoming increasingly popular in AI applications such as image recognition and natural language processing. They have the potential to revolutionize the field of deep learning by providing efficient and effective neural network implementations.
Absolutely. Now let's dive into the main points of the article. One key concept in BWNs is the representation of weights using binary values. This means that weights can only take on two values, either -1 or +1. This binary weight representation simplifies the arithmetic operations involved during forward and backward propagation in the network.
That's right. And not only does this simplification reduce computational complexity, but it also leads to a reduction in energy consumption. By eliminating the need for multiplication operations, BWNs are able to operate more efficiently and consume less power. This makes them a viable option for various computing applications where energy efficiency is a major concern.
Additionally, the binary nature of weights in BWNs allows for efficient memory usage. Since each weight is represented by only two values, the storage capacity needed for weights is significantly reduced compared to traditional neural networks. This reduction in memory requirements makes BWNs suitable for deployment on resource-constrained devices such as edge computing platforms.
However, it's important to note that there are also drawbacks to binary weight encoding. One drawback is the loss of precision in weight representation, which can negatively impact model accuracy. The binary nature of weights reduces the learning capacity of the network. Another challenge is introduced by the binarization process itself, which adds nonlinearities to the network and can make training binary weight networks more challenging.
Absolutely. Now let's shift our focus to binary activation functions in BWNs. These activation functions play a vital role in determining the network's performance and efficiency. One popular choice is the binary step function, which assigns a value of 1 to inputs greater than or equal to 0 and a value of 0 otherwise.
Another commonly used binary activation function is the sign function, which assigns a value of -1 to negative inputs and a value of 1 to non-negative inputs. These binary activation functions allow BWNs to operate with binary weights and activations, reducing memory requirements and computational costs while maintaining reasonable accuracy levels.
However, it's important to note that the binary nature of these activation functions can lead to a loss of expressiveness and gradient information, which may impact the learning capabilities of the network. This is an ongoing challenge in the field of BWNs, and researchers are working on developing new techniques to overcome this limitation.
That's right, and speaking of techniques, there are different types of binary activation functions with their own applications. The sign activation function simply returns a binary value of either -1 or 1, depending on whether the input is negative or positive. On the other hand, the step function outputs a binary value of 0 or 1, only considering inputs above a certain threshold.
These binary activation functions are particularly useful in applications where memory and computational efficiency are critical, such as in edge computing and resource-constrained devices. They allow for efficient computation and storage by reducing the number of bits required to represent weights and activations.
And let's wrap up by reiterating the main advantages of BWNs. They offer significant benefits in terms of computational efficiency and memory savings. By binarizing the weights, BWNs drastically reduce the memory footprint required to store the model parameters. This enables efficient deployment on resource-constrained devices such as mobile phones and embedded systems.
Moreover, the binary nature of weights enables efficient bitwise operations during both forward and backward pass computations, leading to a substantial reduction in computational complexity.
However, it's worth noting that BWNs may suffer from a loss in accuracy compared to their full precision counterparts. But recent advancements in training algorithms and techniques like stochastic rounding show great potential in mitigating this issue.
Absolutely. And with continued research and development, BWNs have the potential to revolutionize the field of deep learning by providing efficient and effective neural network implementations. One of the major challenges in training BWNs is the non-differentiability of binary weights. Traditional optimization methods cannot be directly applied. But don't worry, there are several training techniques that have been proposed to address this issue.
One widely used technique is the straight-through estimator, ST. It approximates the gradient by using the identity function during the forward pass and then applies binarization in the backward pass. This allows for straightforward gradient calculations and has proven to be successful in training BWNs.
Another technique is binary connect. It applies stochastic quantization to enforce binary weights during training. By quantizing weights to only two possible values, -1 and 1, binary connect significantly reduces memory storage and computational requirements while preserving the benefits of binary weights.
In addition to these techniques, BWNs can also be trained using regularization methods such as L1, L2, or sparsity-inducing penalties to encourage sparsity in weight values. These techniques play a crucial role in ensuring effective training and optimization of BWNs.
However, it's important to note that training BWNs comes with its own set of challenges. The binary nature of the weights limits the expressiveness of the models and makes it difficult to approximate complex functions and capture fine-grained details.
Moreover, the training process for BWNs involves non-differentiable operations, such as the binarization of weights, which makes standard optimization algorithms ineffective. So, designing efficient training strategies for BWNs is essential to ensure acceptable performance levels without compromising the benefits of binary weights.
One of the strategies for training BWNs is gradient-based training. This approach aims to determine optimal binary weights and scale factors by minimizing the loss function. However, directly applying backpropagation to compute gradients of binary weights is challenging due to their discontinuity.
To address this issue, the straight-through estimator, STE, technique is commonly employed. It involves bypassing the quantization process when computing gradients during backpropagation. Instead, the gradients are computed based on the continuous values of the weights. This simplifies gradient calculations and allows for effective training with binary weights.
Another training strategy is deterministic training, which applies binarization deterministically during both the forward and backward propagation. This technique avoids the need for approximations and is computationally efficient.
It's worth mentioning that there have been variations and modifications of these training techniques developed for BWNs. For example, the differential straight-through estimator, DSTE, method improves upon the STE technique by introducing a differential operator to approximate gradients more accurately.
These variations and modifications have proven to be effective in improving the training process of BWNs and achieving superior performance in various tasks. One advantage of using BWNs is their computational efficiency. Because BWNs utilize binary weights, they require less storage and computation power compared to traditional neural networks with real-valued weights. This makes BWNs a great option for resource-constrained devices or applications where efficiency is crucial.
However, there are limitations to BWNs as well. The binary nature of the weights can result in a loss of information and reduced model capacity, making it more challenging for BWNs to achieve high accuracy on complex tasks. Additionally, the binary weights can lead to gradient instability during training, further affecting the performance of BWNs.
Despite these limitations, BWNs have proven to be effective and efficient in various applications. They have shown promising results in reducing memory footprint and computational requirements by employing binary weights. This efficiency is achieved through the binarization process, which quantizes the weights to either +1 or -1, greatly reducing the memory storage needed for each weight.
The binary nature of the weights also enables fast computations and parallel processing, improving the overall efficiency of the network. This combination of effectiveness and efficiency makes BWNs a viable option for resource-constrained systems that require high-performance deep learning models.
BWNs have also demonstrated remarkable capabilities in different applications. In computer vision tasks, such as image recognition, BWNs have shown promising results. Their ability to efficiently compute and store binary weights allows them to process large amounts of visual data with minimal resource requirements.
Additionally, BWNs have been effective in machine learning tasks like natural language processing and speech recognition. By leveraging the binary weight representation, BWNs can accurately model and classify complex patterns in textual and auditory data. They've also shown potential in improving the energy efficiency of neural networks, making them attractive for resource-constrained devices.
So we can see that BWNs have a wide range of applications. They have been applied in computer vision tasks, such as image recognition, object detection, and segmentation. Their binary representation offers energy-efficient solutions for these tasks, making them ideal for devices with limited resources.
BWNs have also been successfully used in natural language processing tasks, like text classification and sentiment analysis. As BWNs continue to evolve, they are expected to find broader applications in areas like autonomous driving, robotics, and healthcare.
Another method for reducing the computational complexity of deep neural networks is through the use of binary weight networks. By binarizing the weights of the network to either -1 or +1, binary weight networks achieve significant memory and computational savings while maintaining good accuracy performance.
This process of binarization replaces real-valued weights with binary values through a quantization process. With the use of BWNs, image classification and recognition tasks can be performed more efficiently without sacrificing much in terms of accuracy.
In conclusion, the use of BWNs in deep learning models for image recognition tasks has shown promising results. BWNs offer an efficient solution for reducing the computational complexity and memory storage requirements in deep neural networks.
By representing the weight parameters as binary values, BWNs make it possible to perform complex image recognition tasks on resource-constrained devices without sacrificing accuracy. Experimental evaluations have demonstrated the effectiveness of BWNs in achieving comparable or even superior performance compared to their full precision counterparts.
Furthermore, deploying BWNs in real-world applications can lead to significant energy savings and faster inference times, making them a valuable addition to the deep learning toolbox. The article also highlights the potential of BWNs in natural language processing tasks. BWNs have the ability to process large amounts of text data efficiently due to their compactness and energy efficiency. This opens up possibilities for applications such as sentiment analysis, language translation, speech recognition, and text generation.
Absolutely, and it's worth noting that BWNs have been compared to other weight encodings used in natural language processing. While some encodings offer better precision, they often come at the cost of increased memory usage and computational complexity. BWNs, on the other hand, provide a balance between memory efficiency and computational simplicity.
Moving on to another exciting application, the article discusses the intersection of autonomous vehicles and robotics. With the increasing popularity of autonomous vehicles, there is a need for advanced robotics to enable these vehicles to navigate and operate efficiently.
That's right. Robotics plays a crucial role in developing perception systems, control algorithms, and decision-making capabilities for autonomous vehicles. And this is where BWNs come in. They offer efficient computation and storage requirements, making them a great option for resource-constrained devices. BWNs have shown promising results in tasks like image classification and object detection, enabling real-time decision-making in autonomous systems.
And it's not just about efficiency. BWNs also exhibit robustness against adversarial attacks, which is crucial for safety-critical applications in autonomous systems. This makes them even more suitable for deployment in these domains.
Absolutely. However, it's important to consider the benefits and challenges associated with using BWNs in these domains. One major benefit is the significant reduction in memory storage requirement. BWNs only require a single bit of representation for each weight, compared to the traditional floating point weights. This allows for efficient deployment on resource-constrained devices and faster inference speeds.
But there are also challenges. BWNs lack sufficient precision to capture fine-grained information, which can affect the training process. The binarization process introduces a non-differentiable operation, making gradient-based optimization techniques less effective.
And one important limitation to keep in mind is the reduced representational power of BWNs compared to traditional neural networks. The binary nature of the weights limits the range of values they can take, which can lead to a loss of information. This may be a concern for tasks that require fine-grained discrimination.
Absolutely, it's crucial to consider this limitation when deciding whether to implement BWNs in applications that demand high precision and detailed analysis.
So, in summary, BWNs have shown great potential in various domains, such as image classification, natural language processing, and autonomous systems. They offer benefits such as reduced memory storage requirements and faster inference times. However, there are challenges related to training and precision that need to be considered.
Exactly. One of the key limitations and challenges of BWNs arises from their binary nature. The binary representation of the weights restricts the model's ability to capture fine-grained details and subtle variations in the data. This can result in reduced accuracy and suboptimal performance, especially in complex tasks that require nuanced information processing.
That's right. The binarization process incurs a loss of information as it discards the fractional values present in real-valued weights. This loss of precision can further impact the model's generalization and its capacity to handle diverse datasets. So it's important to carefully address these limitations in order to maximize the potential of BWNs.
Absolutely. And it's not just about accuracy, but also about performance. BWNs have shown promising results in terms of memory usage and energy efficiency, but they often suffer from a decrease in accuracy compared to full precision models.
That's correct. The binary weight encoding can also lead to an increase in inference time due to the extra computations required during forward and backward passes. So while BWNs offer potential benefits in terms of resource utilization, careful consideration must be given to their impact on model accuracy and performance.
Another important consideration is scalability. The binary nature of BWNs leads to a reduction in memory footprint and computational complexity compared to traditional neural networks. However, as the network size increases, so does the computational burden, as binary operations require additional computation compared to their real-valued counterparts.
Yes, exactly. To address these scalability issues, researchers have proposed techniques such as network pruning and quantization, which aim to reduce the model size and computational requirements while maintaining acceptable levels of accuracy and performance.
Now let's talk about promising future directions and research areas for BWNs. One potential avenue is the investigation of novel techniques for enhancing the training efficiency of BWNs. This could involve introducing dynamic learning rates or utilizing advanced optimization algorithms.
That's a great point. Additionally, exploring the integration of BWNs with other emerging technologies, such as neuromorphic computing or quantum computing, could unlock new possibilities and improve overall performance. These technologies offer unique advantages that could complement the binary weight encoding scheme.
Absolutely. Furthermore, investigating the applicability of BWNs in specialized domains, such as healthcare or finance, can address unique challenges and deliver personalized solutions. These research areas hold substantial promise for the future advancement and widespread adoption of BWNs.
That's right. Now let's discuss some techniques that can be employed to improve the accuracy and efficiency of BWNs. One such technique is the utilization of stochastic rounding during the weight quantization process. This approach introduces randomness to the rounding process, allowing for a more precise representation of the real valued weights.
That's an interesting approach. Additionally, techniques like dynamic scaling and weight compensation have been explored to further enhance the accuracy and efficiency of BWNs. These techniques aim to optimize the scaling factors and minimize the potential loss of information during the training and inference processes.
It's important to note that these techniques are still being actively researched and developed. As the field progresses, we can expect more advancements in improving BWN's accuracy and efficiency.
Absolutely, and it's exciting to see how BWNs will continue to evolve and be applied in various domains. The potential benefits they offer in terms of resource utilization and computational efficiency make them an intriguing area of research.
Definitely, but it's important to address the limitations and challenges we discussed earlier to ensure that BWNs can reach their full potential. With continued research and innovation, we can overcome these challenges and pave the way for wider adoption of BWNs in the future.
Absolutely, Samantha. One of the key takeaways from the article is that BWNs have shown promising results not only in computer vision tasks, but also in other fields and domains. For example, they have been successfully used in natural language processing tasks like sentiment analysis and text classification.
That's right, Ben. BWNs have also shown potential in healthcare applications, including disease diagnosis and drug discovery. This versatility in application domains highlights the effectiveness and potential of BWNs as a powerful tool in numerous fields beyond just computer vision.
And it's fascinating to see how BWNs address the trade-off between accuracy and memory utilization in neural networks. By utilizing binary values to represent weights, BWNs greatly reduce memory requirements compared to conventional networks.
Absolutely, and not only that, BWNs also offer computational advantages by employing binary operations that can be executed on digital circuits with low latency and power consumption. This makes them highly efficient and suitable for resource-constrained environments.
However, one of the challenges with BWNs is their non-differentiability due to the binary representation of weights. This makes the training process more challenging compared to conventional networks. But despite this drawback, BWNs have still shown promising results in various tasks like image classification and object detection.
That's true, Ben. And in conclusion, BWNs have emerged as a promising approach for reducing the computational complexity and memory requirements of deep learning models. By using binary weights, BWNs enable efficient convolutional neural networks, CNNs that achieve competitive performance with minimal precision loss.
And while there are challenges in training and optimization, recent research has shown promising results in addressing these limitations. This means that with further investigations into training techniques and network architectures, we can fully exploit the potential of BWNs and unlock their benefits across various domains.
Absolutely, Ben. And another important point is that the adoption of BWNs in real-world applications can significantly alleviate the demand for high-end hardware and energy consumption. This makes BWNs not only efficient, but also more sustainable.
That's true, Samantha. And as we wrap up, it's important to highlight the significance and potential of BWNs in the context of artificial intelligence. They offer increased efficiency, reduced memory requirements, and potential for more energy-efficient hardware implementation. This makes them a highly desirable option for various AI applications.
Absolutely, Ben. Continued research and development in BWNs is crucial to further explore their potential and overcome the challenges they present. By doing so, BWNs can become a viable and practical option for various applications, ranging from edge devices to large-scale data centers.
Well said, Samantha.